First, we look how to build a simple machining model. We started with what things are needed: workpiece, cutting tool, and some fixtures. So, essential steps will be one should have knowledge of geometry and assembly. So, geometry means we have only two parts here. One is workpiece, other is tool or cutting tool. So, I should know geometry of it. We'll talk more detail in further slide. Then what material model? So that is constitute relationship for workpiece, for tool. Then appropriate meshing techniques, appropriate element types, its shape, its size. Then as this is the machining process, cutting tool will essentially have contact with the workpiece. So what type of contact formulation, which surfaces will going to be in contact, that I should have understanding. Boundary conditions, maybe process parameters like cutting velocity or initial temperatures, and then fixing the workpiece, that will all comes under boundary conditions. So basically, I should have knowledge of these five things before directly opening in software. So don't directly open your software and start building. First do some pen and paper work. See, I have all this information available. If yes, material, I will definitely uh, tell you details of each and everything. So we'll know in each of these steps what more information I am needed. So we'll start with geometry and assembly. So in geometry and assembly, one very important thing is choose a coordinate system properly, because uh, after this machining model I will tell you in later sessions laser assisted machining also. That time your moving heat source will travel in which direction, positive x or negative x. It will be very confusing while writing subroutine that time. So it is better while developing a machining model itself, choose your coordinate system wisely. Means now see, if this is my cutting tool and it will move in this direction, means my cutting velocity is in negative x direction. So velocity, okay, or we'll simply call it as a v, cutting velocity, it is in the negative x direction. Let's say minus 200 meter per second, right? Because cutting tool is moving in the negative x direction. If you want to apply it as a positive value, your geometry should be, or your cutting tool should be this side, like this, and it should move in this direction. Similarly, your laser spot also in later sessions I will show you. So the essential thing is choose your coordinate system wisely, and then workpiece geometry. In workpiece geometry, one should know the length of workpiece, this value, at how much length I want machining, what is the overall thickness needed, because some heat generation will happen due to machining. Stresses should not go up to the boundary of the workpiece up to here. So at least choose some sufficient thickness of the workpiece. One more thing we can see here, this line. So don't confuse with this line. What is this? We'll talk in detail. I am just partitioning it. So just a partitioning. Okay. partitioning the workpiece, because that will facilitate us for refined mesh in the zone of interest. This is our zone of interest, because here cutting tool will engage with the workpiece and chip formation will happen. So I want very good mesh only in that region. Below region, it may be a coarser mesh. So this partition, choose appropriately, at least twice or thrice than the undeformed chip thickness, this value, or this is also called as feed. So at least twice to thrice of the feed value. So we can partition it. So this is about the workpiece geometry, a length, the width of workpiece, and the thickness of workpiece. Width is anyhow in third direction. That is definitely we should know, because that will also will give in the section definition in Abacus. So although we have modeled machining as a 2D process here, but our third direction, while I was explaining plane strain condition, that width of the chip remain constant before and after. But that width value, or in machining terminology, that is a depth of cut for us. So that width is essentially a depth of cut. So three process parameters are there: feed, speed, and depth of cut. So this width is a depth of cut basically. This value is feed. Means what is the engagement of cutting tool with the workpiece? The thickness. That is feed or undeformed thickness. And the last one is the speed. That is V, cutting tool velocity. So three process parameters. Cutting speed, feed, and depth of cut. Now everybody having understanding of it. Depth of cut we can cover it with the width. Cutting velocity can directly apply to cutting tool, and feed as engagement of cutting tool with the workpiece. Up to what engagement we are thinking. Then we'll see tool geometry. So as at least in 2D, we can model three things. One is rake angle, flank angle, and the cutting tool radius. So this angle basically, let's say this is the flank surface. This angle is called as flank angle. And this radius at the cutting edge, this is cutting edge. Okay. So I will zoom it here. So this cutting edge may be sharp, or this cutting edge may be having some radius. Right? Two possibilities are there. So this is called a sharp cutting tool. This is with cutting edge radius. Okay, this is not a nose radius. Okay, many people having confusion with nose radius and cutting edge radius. So radius of the cutting edge, we call it as a cutting edge radius. So let's say I will call it as a R. So in tool geometry, basically we can model three things in orthogonal cutting: rake angle, this is rake angle, then flank or clearance angle, and third is cutting edge radius. So these all things are already known for a given cutting tool, or if not, you can measure right in lab what each angle is. Then partitioning, I already explained it. Partitioning we define for better mesh in zone of interest. Uncut chip thickness or feed, that is F, we already discussed this under process parameters. And lastly, coordinate system. So we should start with coordinate system actually. Choose appropriate coordinate system and then define the workpiece geometry, tool geometry, define your section properties, that is width of cut or depth of cut. In assembly, engage your cutting tool in such a way that we can actually taking care of feed value.